And welcome to Module 2. Congratulations, you made it through the first module and you're well on your way to becoming experts in meteorology. So today and for the next few lectures, we're going to be talking about heat and temperature. And this is important because it's this heat, it's this energy that we get that really fuels everything that happens in our atmosphere. And so all the weather, all the interesting phenomenon that we see in the atmosphere wouldn't be there if it wasn't for heat. So let's jump in. So for this first lecture, we're going to talk about heat transfers. Some of you have probably heard of some of this stuff. For some of you, this is going to be brand new. But hey, we're going to jump into it together either way. And this is coming from pages 30 through 35 in the textbook. So make sure you skim those after watching this video. And of course, reach out to me if you have any questions. So let's jump in. Before we can really understand what heat is, we also need to know what temperature is. And so that's our first goal for today. Then we're going to talk a little bit about how heat travels and the different types of heat transfer. And once we've done that, we're going to get into sunlight and some of the more interesting things in the next lecture. So let's do it. So first we need to talk about temperature. Now, I'm sure that you've probably defined temperature at some point in your life as the amount of heat something has, or how hot or cold something is. And the fact is that those things are pretty relative. And while they definitely do have a connection with temperature, they themselves aren't temperature. So here's what I want you to do. Do me a favor right now. Look at any object on your desk or wherever you're at right now, whether it's your computer, whether it's the book, whether it's a bottle of water or the desk that you're sitting at or anything. And think about the fact that each one of these objects is what we call matter. And matter is made up of trillions and trillions and trillions of tiny molecules. Well, the fact of the matter is that each one of these molecules is moving. As we speak, each one of these molecules is actually moving. And the temperature is actually the average speed, the average kinetic motion of that object's molecules. So every object around you is made up of trillions of molecules that are moving, and the temperature of that object is defined as the speed of the molecules. Now, with that said, there's a pretty simple relationship between speed and temperature. Warm objects have fast-moving molecules. So that hot dinner that you had last night, if you had a hot dinner, or if you eat salads, but those warm objects have fast-moving molecules. On the other hand, if you get a bottle of ice-cold water from your fridge that's cold, the water molecules are very slow-moving. Now, with this definition, there's another important definition I need to mention called absolute zero. Now, many of the temperature scales that we use in our everyday life don't actually have an absolute zero. There are negative temperatures. The Fahrenheit scale, the one we use here in America, has negative temperatures. The Celsius scale, which pretty much everybody else uses, also has negative temperatures. But there's actually a temperature scale called the Kelvin scale that has a temperature called absolute zero. You can't go any lower than that. And at that temperature, there is no molecular motion. All of the objects surrounding you have molecules that aren't moving in that case. Now, absolute zero is a theoretical concept, at least here on Earth. And as a result, there's really no absolute zero objects here on Earth. Now, we've gotten really, really close to absolute zero, but haven't gotten there yet. So, just a quick review. Cold objects have low movement. Warm objects have very fast movement of molecules. Or, more lighthearted view, you have these different water molecules. And when temperatures are hot, they're bouncing off of each other, they're running into each other. On the other hand, if the temperatures are really cold, they are slowly moving by each other, saying hi to each other. Some of them are getting together and sticking together and having little water babies and so on and so on and so forth. But fast molecules, high temperatures. Slow molecules, cold temperatures. Now with that said, now we can talk about heat. Heat actually has to do with temperature. Heat exists because of temperature imbalance. Think about this right now. Your body has an average temperature of about 98.6 degrees. Most of the objects surrounding you right now aren't that warm. The chair you're sitting on isn't really that warm, or the desk that you might be touching, or even your computer might not be that warm. Maybe the interior of your computer is, but it's really not that warm. Well, because of these imbalances of temperature, heat exists. Heat is energy that travels between objects of different temperatures. And the way it works is heat travels from the warmer object to the colder object until the two have the same temperature. So, in a sense, heat is very, I guess I'll use the word communist, in a sense, where heat likes to share. Objects like to share their heat until everything has the same temperature. We call that property, when everything has the same temperature, thermal equilibrium. So the way this works, take your hand, either hand is fine, and place it on something. And when you place it on that something, if the two objects don't have the same temperature, heat will transfer from the warmer object to the colder object. And it'll continue to do so until the two have achieved thermal equilibrium, until the two have the same temperature. It's one of the reasons why when you get up from your seat might feel a little warm, because body heat has transferred from your warmer body to the colder seat. And so that's how heat transfer works. And thankfully heat transfer works this way because this is how we can warm up things in our ovens. If you have a ice cold DiGiorno pizza from the freezer, you can throw it in the oven and heat will transfer from the hot air in the oven to the cold pizza. And heat will continue to transfer until the two have the same temperature. So it's exactly what happens when you take a cold object, you put it in a hot oven, heat transfers from the hot oven to that cold object and will continue to transfer until they have the same temperature. Which in the case of a pizza, you don't want that. If they have the same temperature, you're going to have a very burnt pizza. So the idea here is that if you have two objects, one that's hot, one that's cold, heat will transfer from the hot object to the cold object until the two have the same temperature. Now, there are two types of heat that we're going to talk about in this course. The two types of heat are called sensible heat. That's heat that you can actually feel, you can sense it. You can feel it transferring from one object to another. You feel it when you put your hand on a colder object. That's why your hand might feel a little cold. And then there's what's called latent heat. Latent heat is heat that's hidden in the bonds of water molecules. Now, latent heat's a little bit more complicated, but it's very essential to the atmosphere. We'll talk more about latent heat in the next module, in the next module. With that said, the way latent heat works is water absorbs heat when it evaporates, and water releases that heat when it condenses. But like I said, we'll cover that more in a future module. Let's talk about sensible heat today. Now, in terms of sensible heat, there are three types of sensible heat transfer. Probably already heard them, but if you haven't, it's a good chance to get to know them, love them, be one with them. They're called conduction, convection, and radiation. Now, conduction is when heat transfers from one object to another object through a medium called a conductor. some intermediate object called a conductor. The intermediate object is usually a solid object, and heat travels from warm object through the conductor to the cold object. Warm object through the conductor to the cold object. In this process, none of the objects have to move. So there's no movement of the objects, just movement of the heat. Now, even though I mentioned that most conductors are solid objects, there are some that aren't. Air is a poor conductor, meaning it doesn't really do a good job at transferring heat from one location to the other. Conduction can only heat air up to maybe a few centimeters away. Other conductors, such as water, are also relatively poor conductors. So here's the way conduction works. Let's say you have a candle and you have it lit, and you have some kind of metal rod. Maybe you are at a bonfire and you want to cook marshmallows, and you hold that metal rod over the fire. What actually happens is the fire is very hot. Your hand holding that metal rod is very cold. Well, heat transfers from the hot fire into the metal rod and through it to your hand. And heat will continue to do that until the two objects have the same temperature. So conduction involves some kind of direct contact, and it involves some kind of conductor. Now, there are many things we don't want heat to transfer through. For example, imagine if, let's say, as you're watching this, it's 110 degrees outside. You probably don't want the inside of your house to be 110 degrees. You don't want the heat to be conducted from the hot air outside to inside. So what you do is you make sure that your walls are built with poor conducting materials. These are called insulators. And then that keeps the heat from getting through the walls and into your house. So it's sort of how conduction works. Heat travels from one location, from one object, through a conductor to a cold object. Now, another important type of heat transfer, and we see this a lot in our atmosphere, is what's called convection. Now, convection involves movement, whereas conduction, none of the objects were moving. Convection actually does involve movement. In this case, you have some kind of a fluid, and believe it or not, the air surrounding you right now is a fluid, and you have some kind of fluid, and heat is traveling from one location to another by way of this fluid, by movement in this fluid. Now, convection involves vertical movements. So basically what happens is heat near the ground rises in a case of convection. Heat from the ground rises in the case of convection. A good example of this is if you've ever boiled water before and you've seen little bubbles rising up in your water, that's an example of convection. The way it works, heat rises from the surface up through this fluid, and as it rises, it's not rising into empty space. Remember, air has weight, air has molecules, air is a fluid. And as a result, as this air rises, it has to push air away. Well, the way it works is it actually pushes the colder air away and forces it down. So as heat rises, cold air comes in and takes its place. That cold air then gets heated and it rises. And it creates what are called thermals. Basically, you have these bubbles of warm rising air, and then adjacent to them, you have areas of cold sinking air. And they create these circulations that form. So you have hot air rising. As it's rising, it's pushing cold air down to take its place. And then eventually that cold air gets heated up and forms another thermal. Now, this creates a cycle called a convection current. Basically, it works something like this. You have the sun, nice and happy, heating the ground up. As the sun heats the ground up, the ground actually warms the very, very lowest layer. I'm talking the very lowest centimeter or two by conduction. But since air is a poor conductor, heat doesn't get any further than that. But now you have this very warm air that then rises, creating thermals. As it rises, it pushes cold air down. That cold air comes in to take its place. It's then heated up by the ground, and then it rises. And it creates this perpetual circular motion. And so it creates these air currents. Now, if there's any moisture in this hot air as it rises, that moisture might condense and create clouds. The way that it works, and we'll talk about it in a moment, is as air rises, it expands. Well, we'll talk about that in a moment. Thermals are essential if you're a hang glider, or if you've ever had like a plane glider or anything like that. The way that they work is that you have this hot rising air, and that creates substantial vertical motion. As it's creating this substantial vertical motion, if you are hang gliding in that area, that pushes your hang glider up. And so what hang gliders love to do is they love to circle around these warm thermals so that they can continue to stay up in the air. Once they get away from that, they then start sinking and eventually come back down to the ground. So thermals allow these hang gliders to stay up in the air for as long as they want, or as long as the thermals are alive. Now, let's talk about what happens to this air as it rises, because this is actually very important to us meteorologists. As air rises, it expands. The way we can think about this is think about every thermal as a bubble of air that rises. Meteorologists call these air parcels. As these air parcels rise, they actually don't exchange heat or any kind of energy with their outside environment. I like to call this the Las Vegas rule. Whatever happens in the parcel stays in the parcel. With that said, as these bubbles of air rise, they don't exchange heat with their surroundings. But what they do is they expand due to lower pressure. Lower pressure causes them to expand. As they expand, this actually causes energy to be used in the expansion process. As a result, they lose energy, the molecules slow down. This causes the air to cool. So as air rises, it expands and it cools. Now the opposite happens as well. As the air sinks, it contracts and it warms. Make sure you remember that. That is very crucial in meteorology. As air rises, it expands and it cools. As air sinks, it contracts and it warms. And this is actually what happens as air goes up and over a mountain. If you have a parcel of air and you push it up a mountain, as it rises, it begins to expand. As it expands, that then takes energy to cause it to happen. That leads to cooling. As the air continues to rise, it'll continue to expand and continue to cool. Once it gets over the mountaintop and it goes down the other end of the mountain, as it travels down, air pressures increase. That causes the parcel of air to be compressed. That causes it to warm up. So as air sinks, it contracts and it warms. Now, everything I've talked about so far with convection has to deal with vertical movements of fluid. However, horizontal transfers of heat also happen. These are what are called advection. And we're going to talk a lot about advection this class. Air that rises and sinks, that's called convection. Air that moves side to side is what's called advection. And advection is very important because it redistributes heat on Earth. If you've ever felt a cold front blow through and the temperature suddenly dropped 20 degrees, that's because of cold air advection. Warm air was pushed away, cold air moved in. Or if the opposites happen, where the temperatures jumped up suddenly, that's because cold air was pushed away, warm air moved in. Advection is very important because it creates air mass boundaries. When cold air pushes warm air out of the way, it forces that warm air to rise up, which then expands and cools. That cooling leads to condensation, and clouds usually develop. And those clouds eventually develop rain, and so this advection leads to some of the more interesting severe weather that we experience. Now, the last heat transfer I'll talk about in this lesson is called radiation. If you've ever been to a bonfire before and you have felt heat coming off that bonfire, that's what radiation is. The reason why is because you're not touching the fire and you're not touching anything or touching the fire with anything. So there's no conduction happening. There is convection from the fire, but that convection is mainly rising upwards. What you're actually feeling when you feel warmth from a bonfire is you're actually feeling heat going from the fire to your body. That's called radiation. This also happens if you step outside for a moment, when you're done with this lecture, step outside for a moment. And if you feel heat hitting you from the sun, that's also radiation. Now, where do we get most of our radiation from? You guessed it, the sun. And we'll talk more about that next time. So our next lecture, we're going to be talking a lot about this radiation. And let me just say, when I say radiation, I'm not talking about Homer Simpson or Fukushima. We're talking about sunlight, we're talking about colors. There's so many different types of radiation. What makes the difference between one and another? Well, stay tuned and we'll find out about that. Thank you for watching this video. I'm Terrence Mullins. I will see you next time. See you next time.